Right, final thing that we're going to learn about in C1 then is all about our integration. So, integration is the title for your notes, and what I want you to kind of think about integration as being the opposite of differentiation. So, makes sense from a language point of view that integrate something is the opposite of splitting up, of differentiating. We're not going to worry too much about the ins and outs of that for now. In fact, we're not even going to worry too much about where integration comes from. We're going to derive it at some point, but for today, what I want you to make sure that you're happy with is the process and what you need to do in order to apply it. Some notation as well. So if we think about basically, we're going to go the opposite way to differentiating. So if you know what the differential of something is, say you know dy by dx is equal to something like 2x. That could happen. You've got a function, y equals something, you differentiate and you get this result. Now, we need to have a little think about what that might have been beforehand. So we integrate it to find out what that is. So let's just think about what this would be beforehand, before we integrate it. Well, we know when we go from y down to dy dx that, in fact, let's just recap over here. I'll go off to the side and we'll recap. So this one is what I want. So we said when y equals x to the n, x to the power of something n, what happens when we differentiate? We get dy dx, and that equals the n, remember, comes down in front, so the n comes down in front, so it becomes n multiplied by x to the power of, and if we remember, that number, whatever this is up here, decreases by 1, so it goes to the power of n minus 1. Now, let's just concentrate on this bit to start with. Obviously, if we're going the other way, if we're going from dy dx up to y, then whatever we've got value here moves up 1 to our original function. So, that's quite nice. We can see here, on the one that we're using, first of all, let me write in my x, and then we'll think about what comes around it. We've just said that whatever this is, it's going to have to go up 1. Now at the moment it's actually 1. We don't tend to write it as 1, but it's going to be going up to a2. Now if we think about this a little bit, that's a bit untidy, let's rub him out. Think about this a little bit. We've got, that's a nice 2. We've got a function here, y equals x squared. Think about what we would do to differentiate that. That 2 would come down. That 2 would come down here, and then it would decrease to 1, so we didn't write it. And in fact, that would give us what we've got here as our differential. So that's quite nice, a quite nice easy case. But effectively what we've done is we've integrated. I've integrated this to work out what the function would have been before. Now, something else that I need to consider is if we had, say for example, I'm going to go off to the side again one more time, I'm going to work in red this time. If we had, for example, I don't know, y equals x squared plus 3. In this case, dy dx would also equal 2x. So, if I was to differentiate dy dx equals 2x, well, that's what we started with. Dy dx equals 2x, and we integrated it to get y equals x squared. But here we've said y equals x squared plus 3, and that's because this constant here, the number on the end, gets lost. Because of that reason, whenever you integrate, because you don't know whether there was any number at the end, and you also don't know what that number might have been, we always write, whenever we integrate, plus c on the end. So, to integrate, you do the opposite of differentiating, and then you put a plus c on the end. Let's just go through one or two of these with a slightly trickier examples so that we can get our rules in place for exactly what we need to do when we integrate. Okay, so let's call this how to integrate any function, or not any function, how, or the process of integration. Okay, we've already said that the power goes up 1. What I want to do is show you that in a general case. So we've got our dy by dx differential function might be equal to something like x to the power of n. Okay, now let's think about what that would go to when we do when we integrate it to get y. Okay, so y equals, now we already discussed that this n goes up 1. So if it's the differential is x to the n, the integral, the y, will equal x to the power of n plus 1. Now, the other bit you need to work out is really this coefficient, which kind of sorted itself out in that first example I showed you. Let's just make sure this, yeah, there we go, that end's tidied up a little bit. Now, if it wasn't nice and easy and the numbers didn't just cancel each other out and it seemed to work like it did previously, what you'd have to do is multiply it by 1 over n plus 1. That's your formula really for the process of integration. And obviously, as I said at the end, you're always going to add a constant of integration. Let me show you exactly how this works using a couple of numbers. But this is our formula, this is the thing that we're going to apply now. And we'll use it with some numbers so you can see what's happening. Okay, so let's move down a little bit. Where are we? This one. Okay, move down a bit. Let's just try and keep our rule here, and we'll do a couple through. Let's try and find a nice different colour. Let's go for this one. Okay. Oh no, that's not going to stand out. That should work a little bit better. Okay, so let's integrate the differential function. We might have dy by dx. That's nice, nice. Pink, is it? Okay, dy by dx equals x to the 5. Let's apply our formula that we've just shown. So y will have to equal, first thing I'll think about is that index number, which is 5. It's got to go up 1. So it's going to go up from 5, obviously, to 6. That's nice. Now, whatever that number is, that n plus 1, we multiply our x, our coefficient of it, by 1 over that n plus 1. So, in this case, the n plus 1 is 6. So the number in front of the x is just 1 over 6. So it's 1/6, oops, wrong, 1 over 6 x to the power of 6. And that would be the integral, not forgetting, obviously, I guarantee you'll forget it at some point, that we've got to do a plus c, a constant of integration that comes at the end of it. So let's just check and see how this kind of works. Let's just take this function and I'm going to move everything out of the way and we'll differentiate it just to see it working the other way and show that it does work. So if we've got y equals this, we could say dy by dx would equal, well, we know how to do this, we've done this 100 times already. We've got this 6 which comes down to the front, so it's 6 over 6 if you like. 6 over 6 x to the power of 5. Whatever that constant is, I don't know, it could be 1, 2, 3, could be 400, could be minus 5, could be anything, it's going to disappear. And also, if I'm going to tidy this up, I know that 6 divided by 6 is just 1, so it becomes x to the 5. So, hopefully that's what we started with. Yes, you can see that for this function, y equals 6x to the 6, the differential is x to the 5. So I've integrated correctly. I've gone from the differential up to the original function, which becomes a 6x to the 6. Okay, so all I'm going to do now is I'm going to clear everything, just because I want to go through this again and keep this formula here at the top of the screen. So, is everything gone? There we go, right. Okay, let's go for a slightly trickier one so we can see this through one more time. So, the other point that kind of is worth making is your fractions really do help you here. So I'd keep things in fractional form if you can. So let's differentiate let's integrate, I'm getting confused now, a function, a differential function that's a little bit trickier now, with multiple terms as well. So we're going to integrate this, and we're given dy dx is equal to 4x minus x to the minus 2 plus 6x to the half. Okay, same rule again. We're going to go for each function, we're going to go up to use and adopt this thing here. So, let's work out what y would have to equal. Okay, first thing, again, let's look at the index number first. For some reason that's where I always like to start. Here it's 1, we don't write it, so obviously it's going to go up to 2. We've got the 4 there, which I'm going to keep in, and we're going to also multiply by, as we've said in the formula up here, 1 over whatever the new index number is. So that's 1 over 2, so it's going to become 4 over 2 effectively, which we will simplify in a minute. Okay, next term. Leave space for a coefficient, but we're going to increase from minus 2, which goes up obviously to minus 1. And so then we multiply the coefficient by, oops, didn't mean to drag that around, put it back. Multiply the coefficient by 1 over whatever the new index is. The new index number is now minus 1, so it's multiplied by 1 over minus 1. So I'm applying this without a great deal of thought or simplification along the way. We're going to simplify it in a minute. And then plus here, oops, yeah, I can put my 6x in. Okay, first thing, again, I'm going to look at this. It's got to go up 1. So half plus 1 becomes 3 over 2. Okay, now, what I'm going to do, in fact, I'm not going to tidy anything up at all here. I'm going to write this in full. So this first one, again, let's just use exactly the same thing. It's 1 over whatever this is. So it's 1, or because there's 6 there already, that's 6 days, over 3 over 2. Okay. Well, that is a little over thing there. That's not very neat. But never mind. There we go. Kind of works. Let's tidy this up now. Let's bring it down and tidy it up. Ooh, don't forget your plus c. Always plus c on the end whenever you've integrated anything. So, first one's a nice easy one to cancel or simplify. So y will equal, what's 4 divided by 2? The first thing I would do is 2x squared. Okay. Second one I need to simplify. What's minus 1 over 1? Sorry, minus 1 over minus 1. That will become positive, won't it? So plus x to the minus 1. Okay, now, what happens when we divide by a fraction? We've got 6 and we're dividing by a fraction. If you divide by a fraction, you flip it and multiply. So effectively, it will become 2 over 3. Okay, so effectively, let's write this plus. It will be 2 over 3 times 6x to the 3 over 2. Now what can happen? This becomes, what does this become? This becomes 2 times 6, which is 12, divided by 3, which is obviously 4. So let's go down and go out one more time. I of course didn't forget to write my plus c on the end. So what do we got? We've got y equals 2x squared plus x to the minus 1 plus, what did I say this was? It was 2 times 6, which I know is 12, divided by 3, which is 4. 4x to the 3 over 2 plus c. So you can see how, I hope you can see how using your fractions, just leave it in fractional form and things will tidy themselves up. And that's our answer. We've now integrated this fully, so we can underline it because we're finished. Okay, so just have a quick look at what we have done. Let's go out of touch. Okay. Process of integration. If you've got this, dy dx is x to the n, you're going to just follow this rule. And the first thing that you need to do is do your indices first. Increase that by 1, and then 1 over whatever that new number is goes in front of the coefficient. Obviously, you're going to do it, I've guaranteed it, I've done it a couple of times already, you're going to forget your plus c at some point. But make sure that you do remember, ultimately for your exam, because there is always a mark or two through the course of the paper, just writing that plus c on the end. So that's not worth missing out. And there we have it. That is the process of integration. And I'm just wondering whether I'm going to show you a little bit of notation. Do you know, I think I am. Okay, so if you're asked to integrate something, you won't necessarily be given this dy by dx equals and be asked to find y. There's some mathematical notation which we know means to integrate. And so, can we go, just to finish off, I'm going to draw a black line through the work I've done. No, let's get rid of that. Okay. Just to finish off then, let's say down here we'll go with a little title which can be that notation. Okay, and there we are. Okay, so it's all about notation. We call this an elongated S thing here. All that means is to integrate. So you're going to integrate something, and it might be, let's integrate something nice and easy. Let's integrate x cubed, in fact 2x cubed plus x, and work out what it becomes. Okay, the thing that we do is we also put a little dx on the end. What this really means is this bit here, this s, means that we're integrating. Then we put the function. So that's what we're integrating. So we're integrating 2x cubed plus x, and this dx just means that we're integrating it with respect to x, which all that means is we're integrating the x terms, which is kind of intuitive. It'll make more sense when we extend this a little bit further in your studies next year. But for now, all you need to know when you see this is that this bit here means to integrate at the front, and this bit means with respect to x. So probably worth just putting a little notation of that down. So this means integrate, and this means with respect to x, with respect to x. And then this bit in the middle is what you're integrating. So, given that as a question, what would they expect to see? They'd expect to see, oops, let's undo that, get rid of that one, that's not what I meant, just wanted a bit more space. They'd expect to say that this will equal, now if we integrate this, it's going to become x to the 4, it's going to be 2, and that's 2 still there, over 4, and it's going to be plus x squared, the front becomes 1 over 2 plus c. So then I tidy that up. Hopefully you can see where I've got all this from using the formula I've just given you. Equals 2 over 4, I can tidy up to a half. Half x to the 4 plus a half x squared plus my constant of integration. And that would be your answer. So now it's a little heads up of kind of what all this stuff means. Integrate this with respect to x, just basically means integrate this thing in the middle, and don't worry too much about this dx. Okay, and that's us done. 20 minutes. We've now seen integrating, we know the notation, and we're able to do this with all sorts of different types of functions. Fantastic.